We have learned how to solve matrix equations. Now we're going to look at how to find a function given clean data or given data that fits a function exactly. For example, over here I've given some data, both the input and the output. And how could we go about finding the exact function for this data that would fit this data? If you said graph the equation to begin with, that's probably a great start. So if we go to graph, and take a look at that. From what we know from Unit 1, it appears that this is most likely a cubic. We can verify that by coming over here and putting our first difference here. We could say that's equal to that, subtract that one, then quickly fill that down. Well, it's definitely not linear. We could check our second difference and come down here, equals, find the difference in our first differences. Check this out, fill down. It is definitely not a quadratic because we have no constant second difference. Let's see if our third difference can verify what we learned in Unit 1. Equals this one minus that one. And as we hit fill down, it's confirmed to us that this is indeed a cubic. Well, if it is a cubic, it's going to follow the equation y equals ax cubed plus bx squared plus cx plus d. Now, that's the equation that fits cubic. And you'll notice we've got four variables, a, b, c, and d. That is, those become the variables when we substitute in our points. Those 4 points indicate that we need 4 points to be able to determine this exact cubic. Well, it would be reasonable to choose 4 points that would be easy to work with. So as we go here to you'll notice this 0.6 is a very nice one to work with. Let's just highlight that. We'll highlight it with yellow. And let's also pick this particular ordered pair, and we'll highlight it with yellow. And this particular ordered pair we'll highlight with yellow. And we're going to need 4, so let's come down and get one more here, one more ordered pair. And then what we will do is we will take each of these 4 ordered pairs, substitute the x and y values into this equation, this general form of our cubic, to come up with 4 equations in 4 unknowns. So as we do, using that first one, our 0 for x, we get 0 times a plus 0 times b plus 0 times c plus 1 times d, because notice if we substitute x or 0 in for x, it doesn't change the d, equals the y, which in this case is our 0.6. So there's our first equation in our system of linear equations. Now we will substitute in the x value for of 1 in for x. So putting a 1 in for x cubed, 1 cubed is 1. We get 1a plus 1 squared, which is 1b, plus 1c plus the 1d equals, and our y value here is 2.7. Next, we're going to substitute in the 2 for the x. 2 cubed is 8, so we have 8a plus 2 squared is 4, so 4b plus 2c plus 1d equals, and this time our y is 3. And our last and fourth equation, we're going to substitute in the 3 for the x and the 3.3 for the y. So substituting 3 in for our x in x cubed, we get 27a plus, 27a plus, we want 9, that's x squared, 9b plus 3c plus 1d equals, we've got 3.3. So now we've got 4 equations and 4 unknowns. That allows us to make a matrix. Let's strip off those coefficients. 0, 1, 8, 27. Let's strip off the next group. 0, 1, 4, 9. Then we've got 0, 1, 2, 3, and all the coefficients of d are 1. And then we could say that we're going to surround that. There's our coefficient matrix. Our A, B, C, D. There's our variable matrix. We'll highlight it with a border. And then our answer matrix is going to be 0.6, 2.7, 3, and 3.3, and we'll highlight that with a border. Okay, as in past assignments, what we're going to do is we're going to take this and find the inverse of our coefficient matrix. Since it's a 4 by 4, we know we're going to have a 4 by 4 for the inverse, equals matrix inverse, matrix inverse, double click this, select our array where our inverse is, and hold Control Shift Enter. There is our inverse. Now, to verify that that is our inverse, let's quickly multiply it by our original coefficient matrix, equals matrix multiplication. We will multiply the inverse, comma, to separate the arrays, by the original. Control Shift Return, since it's a, you can see that we've got our main diagonal of 1 and all of our other values are 0 or close enough to 0 in scientific notation that it shouldn't make a difference. Now we've got to do the same thing to the other side. Well, let's highlight this quickly, or border this. And we still have our A, B, C, and D here. And now we've got to do the same thing to the other side. So what we'll do is we'll say equals matrix multiplication. We want to multiply that side by the inverse, comma, and times our original answer or constant matrix. Control Shift Return. Okay, we know that the identity times a function does nothing, so all we have is A, B, C, and D here, and down here we've got our point 3, our negative 1.8, our 3.6, and 0.6. So A is equal to 0.3, B is equal to negative 1.8, C is equal to 3.6, and D is equal to 0.6. So now into our original general form, we can substitute those values. We now have y equals 0.3a plus, actually minus, 1.8b plus 3.6c plus 0.6d, and there is our equation. There's a couple of ways we can verify this. One would be to come up here and, if that's our equation, say here's our check column, check, and in this column we put equals. Okay, we said that that was going to be 0.3 times x, which is here, plus or minus 1.8 times, whoops, we've got an error going on here. That is raised to the third, and this one is times x raised to the second, plus our 3.6 times x again, this time to the first power, so we'll just leave it, plus, and our last one was 0.6 for our D. Hit enter. It's a good sign that we got the same answer here. If I now drag and fill down here and we compare the check values with the original outputs, you can see that we do indeed have this correct equation for our exact data that comes from a cubic function.